Hi, welcome back from lunch. Before this next talk starts, just some quick announcements. All of the contests are now running. If you want to play in the security obstacle course over in the Hardware Hacking Village, that is only happening today. So play before 5 p.m., I want to say, 6 p.m., whenever they decide they need to leave, I guess. Later tonight, we have dinner here. That starts at 8. It's a big banquet dinner. If you want to dress fancy, we are all for it, because right after we'll be doing a very large game night. And nothing says class to me like wearing a 3-piece suit and playing Don't Break the Ice and Monopoly and etc. So I hope you guys have fun at that. Other than that, later today we have some more talks in the Lockpicking Village, Hardware Hacking Village. And of course, there's always the chill out room if you need a break from con stuff to play some games and relax. Up next, we have Ignat with Exploiting USB IP in Linux.
Thanks. Hey, do you hear me? Thanks for coming. Hope we got a great lunch. And if you did have a good lunch, please don't snore too loud. Okay, so my name is Ignat. I work for Cloudflare, and today I'll introduce you this interesting piece of technology called USBIP and how it exploited if you use it on Linux, how you could have exploited until some time in the past. And this presentation is interesting by itself, that probably I suspect no one have heard about USBIP, so you'll also learn this exciting stuff. But first, a little bit about myself. I work for Cloudflare. I'm a system engineer. I'm a kind of a security guy. I'm interested in security and crypto. I also like low-level stuff like Linux kernels, firmware, drivers, everything which is implemented in dangerous languages. So, but I'm not a professional InfoSec person, so I'm not a vulnerability researcher. I don't actually look for vulnerabilities. I try to actually build secure stuff, but you may be wondering why then I'm presenting a vulnerability here, because when I do try to use something or use some framework or technology, I try to give it an overview or a sanity look, and that happened to USB IP as well. So what we're going to cover today, I will tell you about what USB IP is. I will give you a quick overview how it is implemented in Linux. Then we will quickly go through how to share a USB device over the network. Then later we will jump to vulnerable USB IP code. We will discuss potential exploit impact. And lastly, I will try to give you some tips if you do want to use this technology, how you should harden your USB IP setup. Okay, let's go. But first, since this is a vulnerability, some of you may be wondering, am I vulnerable to it? So as a quick exercise, how many of you previously heard about USB IP technology? Oh, nice. And how many of you are actually using it? No? And how many of you actually patched your Linux kernel from last year? Good, good, good. So the rule of thumb is here, if you never heard of USB IP and you're sure you're not using it, so you're safe. If you do use USB IP, you're probably reasonably safe. But if you do use USB IP but patched your kernel from last year, you're reasonably safe. And if you're using Linux and you haven't patched your kernel from last year, you probably have way bigger problems. So sorry, I can't help you here. So what is USB IP? It does exactly what it sounds. It's a way to share a USB device over the network. And the good part is it's device or driver agnostic, so it's not tied to a particular type of USB device, so theoretically it can be used with any USB device. And it's implemented by, so it does that, it's being device and driver agnostic because it's implemented in a lower USB layer. What it does is just forwards your URBs over the TCP connection. So if you are not familiar with USB protocol, URB stands for USB request block, which is like the basic unit of data transfer, the basic frame or packet in the USB protocol. So everything in USB world communicates using URBs. And USBIP is actually implemented for Windows and Linux. So here is the very high-level architecture. This picture is taken directly from the project website, where you can, and the link to the project website you can see below. Sorry, no HTTPS, so maybe this data was hijacked. So, but anyway, as you can see from the diagram, USBIP implements a typical client-server architecture, and for the purpose of this presentation, I will briefly describe the roles because it's vital to understand them further. So we have a USBIP server, and in USBIP terminology, server is a site which actually exports USB devices over the network. So server is a site where you plug in physical devices, but the server typically does not use them. On the other hand, a client from USBIP terminology is a site which imports USB devices. So there are no physical devices on the client, but the client connects to the server and imports the device, and after the import information, import operation, the USB device appears as it was plugged in locally to the client. So, and here we see there are user space and kernel space components, and the basic flow how it works, because on the server side we have this USB stub driver which just intercepts all URBs from a particular device, forwards them to the client, and on the client side we have virtual host controller interface driver which injects them back into the client USB host subsystem, and this way you can share any USB device over the network. And as I said, it's implemented for both Windows and Linux. You can download the Windows code on the project website. From Linux perspective, this project was accepted to mainline Linux kernel code since 3.17. So most probably if you have a, coming back. So most probably if you have recent Linux distribution, you have USBIP there supported. Okay, so this how it is implemented directly in Linux components. So as I said, if you have a recent version of Linux, what you can find there, again, you have a user space and kernel space components, you have client and server. So USBIP components are represented in green here. On the server side, in user space, we have USBIPD, which stands for USBIP daemon. And we have two kernel modules, USBIP host and USBIP core. So here, USBIP host is actually what's implementing this stub driver on the scheme. And on the other hand, from the client side, we have USBIP user space client utility. We have, again, the USBIP core driver, and we have the virtual host controller interface driver. So USBIP core driver is like just a piece of shared code between client and server. The project authors, for some reason, decided to move them to a separate kernel module, but think of it like a shared library in the kernel between client and server. So, and the way how it works is, like, imagine we have this client and server setup. Yellow, we have the real server's USB host controller driver, and at some point you plugged in a physical device to the server. What happens then, that USB device will start talking to the USB host controller, and USB host controller will like enumerate this device, means that it will identify what the device is and report to the USB server's USB core subsystem that a new device appeared and it's some of its attributes. And if you have, again, a recent Linux kernel distro, you probably have UDEV, which will automatically load the appropriate device driver for your USB device, and that device driver will start managing the USB device. So this is simple. So now, at this point, you want to export this USB device over the network. So what you do is you just, using USBIP daemon, you send the command down the stack that you want to export this device. So the command reaches USBIP host controller driver, and the driver just disables the device driver and starts forwarding all URB traffic to the USBIP host driver. So, and at this point, the device is considered exportable. So although nobody imports it yet, so the server does not see this device as connected anymore. Then at some point, a client comes in, and client sends a request to the server that, hey, hello, I want to import this USB device. And what the server does, it establishes a logical connection to the client virtual host controller driver and forwards the URBs over there. And virtual host controller driver, again, like behaves like a normal host controller driver, so it just sends a notification to the client's USB core subsystem, hey, I got a new device, here is its like attributes, and again, if you have a new recent kernel distribution, a device driver will be loaded for you, and this driver will start managing the remote device through all this red pipeline. Yeah, and this way how it looks from the shell, this is like client-side view of operations. So imagine we already have a server which exports a device. So from client side, what you would do is you use, everybody sees that? Like, is it large enough? Or? Yes. So you just launch the USBIP client utility. You first launch the list command and put IP address or host name of the server, and you just see which devices are being exported on the server. So now we see that we see one device, and you see here is a product and vendor ID, which is dead beef in this example because it was hijacked. And what we're interested in is so this is like a bus ID and device ID from USBIP perspective. So to import this device to the client, we just issue another command. We say attach. We specify again the host name or address of the server, and we specify which specific device we want to import. And from that point, this device will appear on the client if everything is okay. So when I first looked at this technology, and it seemed to be it's pretty much like any typical VPN, but instead of just forwarding low-level layer 2 Ethernet frames or IP packets, it just forwards URBs. So pretty much like that. And so this is architecture of a typical VPN for Linux. So here, when you have a VPN tunnel, the kernel has a special virtual network Ethernet device, and application sends their traffic to this device. So you always have this VPN agent running in user space, which just reads those. So when application sends some traffic, it passes through all Linux TCP/IP stack, and then gets forwarded to DevNet tune device, and you have this VPN agent which gets this low-level packet, sends them to the other side, and the other side imports them back, and it also goes through the other side's TCP/IP stack and gets forwarded to application. This is a typical example of Linux kernel maintainers call tools in the kernel policy in user space. So because there are so many different VPN protocols and ways to communicate, they don't want every single protocol to be implemented directly in the kernel. What they provide is they provide the framework or the tools to implement any VPN solution in user space. And I was kind of and it sounds like similar as USBIP, and I was expecting similar implementation for the USBIP protocol, but my surprise was that in this example, when you issue the USBIP attach command, the USBIP client utility exits immediately. So it doesn't stay in the foreground on the background, and it just gives you an exit code, but the actual device is being imported and works. And my first thought was like, okay, probably this client utility just forks itself in the background and just stays there. So I wanted to find this background process, this agent, and try to kill it, for example, and see what happens. And when I looked for it and I did some more research into it, I haven't found any process which runs in the background in USBIP Client. So basically, the USBIP Client utility exits, but nothing more is added to the system, which would be the role of that VPN agent, which will forward the traffic. And I was, what? Then I started digging into the source code. So turns out the way how it works is a little bit different. So this is like another view of how things happening. So with the list command, everything is simple. So USBIP daemon just keeps a list of exported USB devices and memory, and when the client sends a request, hey, give me the list of the device, it opens a TCP connection to the server, sends a request, receives a response, displays, exits, done, simple. The interesting part happens when the client tries to import the device. So again, it starts the same way. It opens the TCP connection, sends a request to USBIP daemon on the server side. The daemon does some small housekeeping, verifies the device is still being exported, sends a success response. But after the client receives a success response, they don't close the connection. What they do is both client and server pass the socket file descriptor, which represents a specific TCP connection, directly to the kernel. And after that, actually, the whole network communication is handled by the kernel. So the actual USBIP application level protocol is implemented by the kernel, and kernel is your, let's say, that VPN agent, which is very unusual for Linux kernel implementation. And having an application level protocol in kernel is a very dangerous thing to do, because you have to do some parsing and handling of the protocol, and you're executing in a very high privilege context. So I just decided to dig further and verify the sanity of the implementation. And it went bad, so.
So once you've got the client and the server connected there, can you do an LS USB on the client and CD USB devices as though it were connected?
Yes, yes. So after you import the device on the client, if you do ls USB on the client side, you will see your import devices. So it behaves as you like plugged in the device locally. Yeah, and to give to give you an overview how it works or breaks, this is like a small TLDR of the USBIP application network protocol. So it's very simple. It's the same as any other, like most of other protocols out there. So it has a payload section which contains the actual USB request data being transferred, and it has a header, USBIP specific application header. And as with any other protocol, the payload has a length, and the length is just a field in the header. Simple. And here is the more detailed description. It just has 4 or 6 commands. I think it's very easy to understand. So if you look directly into the Linux kernel, this is like receiving a USBIP packet in the kernel driver. So it contains 2 basic operations. It just parses the header and receives the rest of the data. If you take a closer look at the parse the header section, the interesting part here is that the header is parsed directly into the URB structure. And URB structure is the actual in-kernel representation of the URB. And all of the kernel core subsystems and kernel USB device drivers are using this structure to pass URBs around. So we just parse the header here and put the relevant information directly into the URB structure. And the interesting part is that we parse the length and store it there. And if we take a look at the receive the rest of the data function, so we see that this specific length, which was parsed, is used to initialize a local variable called size, and then this function is called that receives the rest of the data from the socket. So the bad part here is that in between the initialization and receive the rest of the data, this is just like a socket receive function in user space. There is no validation that this pointer to URB transfer buffer size is actually large enough and points to large enough buffer to contain everything, the data of size. So yeah, you have arbitrary lengths. It is possible to write arbitrary length data to URB transfer buffer. And you can write past the buffer boundaries, which is bad. So what is this URB transfer buffer? Where it comes from? So it is, since USB by itself, USB protocol by itself is on the slowest level is only host to device. So even if you're expecting to receive some data from the device, on the lowest level, it's still being done by on request from the host. So typically, this URB structure and associated buffers are allocated by either by USB core subsystem or specific USB device drivers, depending on which stage the USB device is being managed. And technically, when USB protocol by itself did not assume that there will be some malicious attackers on the way of communication, because it's like it's a protocol for communicating physically connected devices. They didn't expect you can do it over the network. And so these sizes, there is no way actually for the host to pre-compute the size of the potential response. So every device driver is just expected to know what is the maximum size of the data it can receive from its managed device, and these buffers are allocated accordingly. So if you just send like a response with a larger size, they are not ready to process it. And if you take a network side perspective, so we are not sending a USBIP packet with a large payload is not in any way a malicious packet or malformed packet from USBIP point of view, because it's just a packet with a large payload, but the length of the payload is equal to the length of the header. So if you will want to use some network analyzer to drop these malicious USBIP packet, they'll be totally valid from the protocol point of view, unless they are have some deep connection tracking capabilities. Yeah, so this vulnerability has received the number CV 2016-3955. It received a very big CVSS base score. This is like a score which is given by US National Vulnerability Database. And although if you don't use, as I mentioned previously, if you don't use USBIP technology and it's very rarely used, you're not vulnerable. If you do use and you are vulnerable, it's very easy to exploit, because it can be exploited from network, and it requires it requires no authentication to be exploited. That's probably why it received a very high score. And I also gave it a nickname called U-Boat, so it's USBIP buffer overflow attack. Although I'm not in favor of giving nicknames and logos to vulnerabilities, practice shows that if the vulnerability has a nickname, it's more easily remembered and it's easily to communicate between security researchers. But unfortunately, I'm a very bad designer, so I don't have any logo. So if somebody wants to contribute a logo, so please contact me. No. Cloudflare does not do vulnerability research, right? It protects from vulnerabilities. But it's not related to any boats, right? I need a submarine logo. I was thinking like that. So what are the requisites to exploit this attack? So the first one is your potential victim has to actually use USB IP. So although the USBIP code is present in the mainline kernel and almost all major distributions, Linux distributions, by default it's compiled as kernel modules, so it's not compiled directly in the kernel. And the kernel modules are being loaded when you start using your USB technology. So if you don't use USBIP, the kernels are not loaded in the kernel, so your kernel is not vulnerable. Victim has to be client in USBIP terminology, so I found this vulnerability on the client receiving pass, not the server receiving pass. So it's currently I haven't found any way to exploit the server side, only the client side. So the side which actually imports the device. And your potential victim has to import at least one USB device. So as I showed previously, so there is some initial communication between client and server, and then they pass the socket descriptor to the kernel. So unless there is this socket descriptor in the kernel and kernel handles at least one network connection, the kernel again is not exploitable. And you as an attacker, you have to either MITM the connection between client and server to change the USBIP packets to send a large payload, or you have to somehow hijack take control of the USBIP server and make it send in different responses. So, demo. So here we have wake up. Here we have a simple Ubuntu. With the only difference is it has a vanilla kernel. So what's the kernel version? Oh, the kernel here is 4.48, which is the last kernel vulnerable from 4.4 series. So and the purpose, to make the demo simple, I just assume that I don't hijack the connectivity. I hijack the USBIP server, so I will not use the standard USBIP server. I will use my custom USBIP server, which is malicious. And again, for the purpose of simplicity, I will not emulate client and server directly. I will just, because network, you can communicate with localhost, which is very handy. I could just use one virtual machine instance to do that. So first of all, I will start the server. I call it Ubuntu server. Do you see these guys, or should I make it larger? Okay, so I started server, and please note that since USBIP is communicating over like port which is about 1024, if I hijack, I don't even, so imagine I hijack the USB server, I don't even need a privileged account. I can just, I run the server from my user account with no privileges on the system. So this here we have the client side. So the client side, we will first check which devices are being exported from the server. Okay, I forgot the list command. Okay, and I have a logging on the server. So here I say that I'm sending fake device list. And from the client side, we see one device is being exported with product and vendor ID of dead beef and physical path sysfake dangerous demo. So, yeah. So now we will try to import this device. So server is programmed in a way that it will, on the first USB URB request sent from the client, it will see that, for example, the client requested 64 bytes, and the first request would be 64 bytes because it's how USB core enumerates devices. And it will just add 512 bytes to the response and sends so the client side would expect a response of 64 bytes, but we will send like much more than that. So first of all, as I mentioned, I have to import modules. Oh, sorry. The USBIP core and Okay, and now I'll try to import this device with super user privileges. So address of the server, and the actual device I want to import is 1/1. Okay, let's see what happens. Ah, I forgot the command name, sorry. Okay, so we see that I have logging on the server, so the client sent a request expecting the maximum response 64 bytes, but I sent him 576 bytes. So did it crash? It has some errors. So sometimes it crashes at once, sometimes it doesn't. So if I see the demask, yeah, I specifically also modified some code to show the demask output. Some kernel code. So this is, although we requested 64 bytes, this is the state of a portion of client kernel memory before the request, and this is the state of the client memory after request. So we see like I overwritten everything with that code here. Okay, and to make I may try to do another test, maybe. Oh, okay. And after second time, it stack trace, so it crashed now. I don't know if I can increase. Yeah, it's just like. I don't know if I can increase fonts here. So anyway, it's stack traced now, and yes, so it doesn't work anymore.
Entire screen at the macOS level. I think that's a control 2-finger up or something like that, or a command 2-finger up.
I don't.
Command plus doesn't work as far.
No, command plus doesn't work. Scale mode, maybe this one.
That's not.
Well, anyway, this system crashed, and we see that it's not responsive anymore. Here. Oh no, here it is still responsive. Ah, no, it closed. So the system died. So it's just a simple attack which overwrites garbage to kernel memory and crashes the system. Okay, how do I go back here? Okay, so how can you exploit it? So as we just saw, we can do a simple denial of service, just crash the USBIP client. You can actually try to do more sophisticated attack and write not garbage but some meaningful data and do data injection or code execution. So it's if you can do data injection, you can do code execution by trying to overwrite portions of memory which contain function pointers, and if you write meaningful function pointer, and once the pointer is the reference, the kernel will execute your code. I will not, but remember that this is a heap exploit. So code execution, when you have buffer overflow in the stack, is kind of easy. You just write past the buffer, you try to override the return address, and you get your code execution. Since the heap memory is kind of a random thing, it's much harder to do code execution when you have a heap exploit, and I will not describe in detail how to do that, but instead I will just refer to this blog post. So this is another old vulnerability in Linux kernel, which also led to kernel heap exploit, and this blog post has very detailed instructions how to do code execution if you have a heap exploit. So it doesn't matter like how do you get to the heap exploit, it matters that you have a heap exploit and you can try perform these steps to get a code execution there. But I'll give a quick overview how it works and how the USBIP exploit makes it more convenient for attacker to do some exploiting of the target system. And for that, I will give a very 1,100 feet overview of how Linux Memory Manager works. So if you want to allocate dynamic memory from the heap, so what Linux does, it reserves some memory in the system, and each memory block is broken to equal parts, which are called slab caches. So the first, as we see, the first range is broken into equal parts of 32. The second range, and it's called slab 32 cache. The second part is broken into chunks of 64. It's called slab 64, and we have slab 128. And it actually doesn't have to be a power of 2. There are sizes in between. It's just shown for brevity. So that we have these different slab caches. And when, for example, if your kernel code tries to allocate a chunk of memory, like say with kmalloc function, for example, it requests 28 bytes, what kernel will do for you, it will just round it up to the first available slab cache and find the first available chunk on that cache and hand it over to you. So in my example, if you requested 28 bytes, you will probably get like this chunk. You will probably actually get 32 bytes, but you don't care because it's more than less. So yeah, and if you have a buffer overflow in kernel heap, what you can do is you can overwrite memory in other chunks. So what are these other chunks? These other chunks may be allocated to different kernel subsystems. So as far as data injection goes, if you can write arbitrary data, you can just overwrite control data or function pointers for other kernel subsystems. And if you're lucky, because this is all like random process, but there are actually ways to ensure that the specific objects you require are in your slab cache, you can just influence the behavior of other kernel subsystems. So when you have depending on what kind of a heap overflow you have, or what kind of attack you can perform, USBIP is very convenient because it allows to write arbitrary amount of data parse, almost arbitrary amount of data parse past your buffer boundaries. What usually attackers do, they only have the ability to write a couple of chunks after a specific slab cache, in a specific slab cache. So they don't. So for example, if you have vulnerability in slab 32 cache, you know your vulnerable code allocates memory in slab 32. What you would normally do is you just scan all the Linux source code and try to find some subsystem of interest which also allocate objects in the same slab cache, and you'll try somehow to come up with an idea how to override the data for that specific subsystem. While USBIP gives you more flexibility, first of all, because of the nature of the vulnerability, you can override almost as many chunks after the buffer if you want to. It greatly increases the probability of success of attack. So if you have only, if you can override only one chunk past the buffer, the probability of your object in that specific chunk is very low, but if you can overwrite many chunks, you increase your success rate. The other interesting point here is the attacker may actually influence the client to allocate buffers in the desired slab cache. So in this specific case, attacker is not bound to a specific slab cache. So instead, he may want to exploit an object in any slab cache, and he can influence the client to actually start allocating buffers on that specific slab cache. So the way how it can be done is that since the attacker already controls the URB traffic coming to the client machine, the attacker can actually emulate any USB device on the client machine. So what the attacker has to do, there are a lot of USB drivers in vanilla kernel source code, so the attacker has to just find the appropriate device driver which allocates buffers in the desired slab cache. Then the attacker it does not perform the overflow immediately, like I did in the example, but instead it sends a valid USB traffic to the client, which emulates that specific USB device. So, and the client will see that, hey, a new device appeared with specific characteristics, and hopefully the UDEV subsystem on the client side will load the appropriate device driver, and that device driver will start allocating objects in the desired slab cache. And after that, only you perform the overflow. So in this point, the attacker can control the client's behavior from which specific slab cache to use to allocate and to move the vulnerability around between slab caches. So still want to use USBIP? Okay, if you do want to use it, like the first thing you should do is reconsider. Because it's still a dangerous piece of technology, and if you just use it, like if you have a small cheap device and you want to share it across computers just for cost efficiency, just buy another device. Yeah. The second thing you should do is patch your system, patch quickly and patch often. It is not related even to USBIP. You should always do that for any systems because vulnerabilities are always found and you have to stay on top. Specifically for USBIP, definitely you should protect your network traffic. So even though if your system is patched and you know more vulnerable to your boot, you still see that if the attacker hijacks the connection between your USB client and server, the attacker can emulate any USB device on the client side. Let's say attacker can emulate, I don't know, a monitor and just capture all your input or capture your screens or emulate a keyboard and do some unauthorized input. So the key to that is that unfortunately, the basic USBIP project does not have any inbuilt security capabilities, so you have to wrap the traffic in a TLS connection with authenticity as a mandatory requirement and preferably encryption as well.
Just to scare people, your USB device could be a CCID profile smart card reader.
Yeah. There are many USB devices out there. I mean, I think you can. People can find.
Does a wonderful job with the crypto, but guaranteeing that there's a smart card somewhere attached via this protocol to your client doesn't prove that it's actually connected to the client.
Yeah. So you can subvert system in many, many ways. And protect your traffic even in intranet, as we saw from previous talks and from previous security conferences, and we will hopefully see in Fail of Things today that even if your home network you think it is secure, you have these fancy IoT devices, and you may never know who is sitting in your intranet. And lastly, ensure that your USBIP server is trustworthy and sufficiently protected with access control, because if the attacker will not be able to hijack your network connection, he will divert his attention to your USBIP server. And again, as we saw in an example, if he controls the USBIP server, it controls the response from the server and can do many fancy things to your system. Okay, here are some resources. So the first link is my original blog post about the vulnerability. It has more detailed code listings and points to Linux kernel code exactly where the vulnerability is and has most of this information in detail. The second one is the source code of my vulnerable USBIP server. So originally as a proof of concept, I wrote it in C because, yeah, I like low-level things. But as you saw that since running a vulnerable bad USBIP server does not require any privileges, just some network connectivity, so I rewrote it in Go. So it's very easy to understand and read. Third one is the entry in CVE database. It has many detailed links into forums, and people are discussing the vulnerability. You can provide more details, and maybe people come up with some other ways to exploit it, which which is not covered here. And the last one is the entry in National Vulnerability Database, which provides a vulnerability CVSS score and has a detailed breakdown why the vulnerability received such a high score. That's it. Thanks. Questions? I think we just handled them in flight, right? No questions? Okay, thank you.